So this is the second version of the previous video, and I'm going to try to make the results here be a bit more clear. So we're talking about a Poncelet 5-periodic family that I can animate, like so. Okay, with 5 vertices, and this family is interscribed between two non-concentric, non-axis aligned ellipses. And all I'm going to do is I'm going to select within this trajectory 3 diagonals. So I'm going to pick a point, say P1 on the trajectory, and I'm going to say, okay, I want to draw 2 diagonals connecting P1 to P3, P1 to P4, and then I want to draw a cross diagonal, say connecting P2 to P5. And I'm going to label P2 as A, this first intersection here as B, the second intersection as C, and the third intersection as D. And I can watch this construction with respect to P1, let's make this a bit slower, evolve. Okay, now of course a natural measurement that can be made here on the sequence A, B, C, D is that of the cross ratio. The cross ratio is the product of distances AC times BD divided by the product AD times BC. So that's the cross ratio in the usual sense. And I can actually watch that cross ratio. I'm reporting it up here, and that cross ratio is varying as I traverse my 5-periodic Poncelet family. Okay? Now the first thing you're going to notice, I'm also reporting a sum and a product. How am I computing these? I'm actually iterating the sort of anchor vertex over all vertices on my family, okay, or on my polygon. How am I doing this? So here you're seeing the original construction, 2 diagonals emanating from P1 into P3 and P4, and the cross diagonal. Let's now repeat this construction, but with respect to P2. So let's illustrate that. Here's a construction with 2 diagonals emanating from P2 and a cross diagonal at the corresponding vertices. So it's the exact same thing if you take the indices into account. I can do the same for P3. So let's now repeat this construction with respect to P3. Here are the 2 diagonals emanating from P3 and the cross diagonal connecting these 2 vertices that are neighbors to P3. Okay, and I can do this for all 5 vertices. And you're going to notice here that I can report the cross ratio defined the exact same way I just mentioned for each one with respect to each one of these base vertices. Okay, so go back to vertex P1. My cross ratio here is 1.74. Go to vertex P2, I got a different number for that cross ratio on these 4 collinear points, 1.322. Go to the third vertex, I get a third cross ratio. Go to the fourth, let's go ahead and walk through all 5 vertices. So here I'm getting 1.31. You can see that these are all distinct numbers. Okay, so let's go back to our first construction with respect to P1. And I'm reporting 2 quantities. I'm summing over all these so-defined cross ratios, that is to say, these 3 diagonals defined with respect to each individual vertex. So I get a sum of cross ratios, 1.50. And I can also report the product. Now the first interesting result here is that with this particular assignment of A, B, C, D, I'm getting this product. And this product is invariant. Now as you know, there's 6 assignments of 4 collinear points. We're going to compute 6 distinct cross ratios that are related to each other. Okay. In fact, there's 24 arrangements of A, B, C, D, but there's 6 groups of 4 arrangements, and in each one of these groups, you're going to end up producing the same kind of cross ratio. So let's look at the second arrangement. Here I have A, B, C, D in this order. Let's look at the second arrangement now when I have A, B, D, C. Okay, now what do I get when I do this? We get a surprise that under this arrangement, both the sum of cross ratios and the product of cross ratios is conserved. Okay, let's go for the third arrangement where I'm going to get A, C, B, D. So this is a third cross ratio arrangement. Now I'm only getting, as you can see here, constant product. Let's go to the fourth arrangement. Now I'm getting in the cross diagonal here, I'm getting A, C, D, B. This arrangement, okay, is also conserving both sum and product of cross ratios. Notice that the product of cross ratios is 3 units above the sum. There's 3 diagonals here. We don't know what the relationship is between these two quantities, but they're separated by 3 units. If you go back to that previous arrangement, I believe it was arrangement 2, where I had A, B, D, C, I'm also getting 3 units of separation, but now the sum is 3 units above the product. Okay, you can see here 3.079, 0.079. So both sum and product of cross ratios are constant, with the sum 3 units above the product. And if you go to that other arrangement, I believe it was this one, ACDB as opposed to ABDC. So I'm looking at ACDB. Okay. This ACDB arrangement also conserves both sum and product. However, the product now is the one that is 3 units above the sum. Okay, so we don't know what this number 3 comes from, but that's pretty interesting. Let's go to the 5th cross ratio arrangement of 4 collinear points. So now I have ADBC. Let's look at what's happening here. Again, both sum and product are being conserved in this arrangement, but we don't see here this integral relationship between the sum or product. Their difference is some other number. And let's go to the 6th and final arrangement, this one over here, ADCB, and let's look at what's happening here. Again, the 6th arrangement is conserving both sum and product, and it's not obvious what the relationship of these two are. Okay, so we have 4 arrangements in this particular setup. Okay, I take a particular point P1 on my Poncelet 5 periodic family, and you can see that this is interscribed between 2 non-concentric, non-axis aligned. So let's say these nested ellipses are in general position, and I have 4 arrangements of 4 collinear points that all of which produce different products and sums of cross products, but where in each one of these 4 arrangements, both the sum of cross products and the product of cross products is conserved. Alright, so in this video I'm only going to cover this n equals 5 case to make it shorter. See you on the next one. Thank you.